All right, so this should be lecture one. So this is going to be review. This should be review from last semester. This is section 5.4, indefinite integrals and the net change theorem. So at the end of last semester, you should have begun talking about antiderivatives and integrals. So the typical integrals we've been seeing have been of the form, integral a to b f of x dx. And what this means is you try and find, so the way we do this is we try to find an antiderivative So we try to find, something that when we take its derivative, we get, the integrand, this f of x here. So we try to find an antiderivative, and then we would do, so let's say capital F of x. And then this integral, a to b f of x dx, would then just be f of b minus capital F of a. So when we're trying to do these problems, we talked about these being areas under curves, and we learned that we could do these just by evaluating some other function at one point and subtracting off another function at another point here, f of a, so f of b minus f of a. So we're going to learn some notation first. So the first thing we're going to learn, and if I'm going too fast, flipping through pages too quickly, you can always pause the video and keep writing. So first thing we're going to do is we're going to talk about the indefinite integral. So if you look back at the previous integral, we had that squiggly sign in a to b there. The indefinite integral, I'm not going to specify an a and b. I'm just going to write integral f of x dx. And that's going to be equal to some capital F of x, where f of x is equal to, f prime of x. So still getting used to this, you'll have to bear with me. Capital F prime of x, so the derivative of this capital F is going to be equal to little f. So all this means is we want to find the general antiderivative. So, for example, if I'm trying to, so if I wrote down integral cosine of x dx, we have to ask ourselves, okay, what do I take the derivative of that gives me cosine? And in this case, it's going to be sine. So I get sine of x. And then I have to, so when I say the most general, anytime I have like an indefinite integral, I don't have bounds here, I have to write plus c, so plus some constant. The reason being, if I take a derivative of this right-hand side, this first term will become a cosine. Derivative of sine of x is cosine of x. But when I take the derivative of a constant, that goes to 0. So I have to add this constant because, this is the most general antiderivative. I don't have to worry about it when I have bounds because when you subtract it off, it goes away. It's not that big a deal. But yeah, so this symbol right here, the integral f of x dx, we're just asking you to find an antiderivative. So one other thing, just to make sure that we're all on the same page, so just a little bit of notation. So let's say I wanted to find the integral from 0 to 1. Let's do x dx. So if I want to integrate this, you do the reverse power rule, x squared over 2. You can check to make sure that derivative, or if I take the derivative of the right-hand side here, I'll get x. And the way I'm going to write this now, so normally I would do, plug in 1 and subtract off when I plug in 0. The way I'm going to write this is I'm going to write 1 and 0 here. What this means is plug in 1 here, subtract off what I get when I plug in 0 here. In this case, it's a half. So just a little bit of notation. And if you look in the book on page 403, you have a big table of antiderivatives. So, you don't have to memorize every single one of them. You'll use a lot of these enough that they'll just stick in your head. You should memorize, the important ones are the ones that, we don't know how to derive yet. So like, for example, if I want to integrate, so if I want to integrate x to the n dx, I know how to do this. It's the reverse power rule. I undo the power rule. I do an n+1 up there, and I divide by n+1. And then I also have my plus c because it's there's an indefinite integral. So things like that you don't need to memorize, but there might be a couple on that table that you might not know how to derive. So you want to, those are the things you want to look at, maybe like arctan, things like that. Okay. So let's do an example. So let's do an actual example. So let's find integral 10x to the 4th minus 2 secant squared x. And I'm integrating all of this. So I'm going to put parentheses around it. And let's do that. Let's do this integral. So one thing you need to know is, just like the derivative, the integral is linear. If I have, a sum in here, I can break this up into integral 10x to the 4th, and then minus, sorry, forgot my dx, and then minus integral 2 secant squared x dx. So I can break up my integral like this, and this makes it a little bit easier. Next thing to know is constants in front of, multiplicative constants. I can pull those out of the integral. So this is going to be 10 times the integral x to the 4th dx minus 2 times the integral secant squared x dx. And right now, we don't have a lot of techniques for figuring these out. So in this section, we're going to be able to, guess what these different integrals are. So for example, if I look at the first one, I can do that pretty exactly. So this is going to be 10, and if I integrate x to the 4th, and x to the 5th divided by 5, again, reverse power rule, and then minus 2 times, and then if I, so I have to, so for this one, I have to think, okay, what do I take the derivative of, and I get secant squared. So if I think back to my trig functions, the derivative of tangent is secant squared. So the integral of secant squared then is tangent x. And then because it's an indefinite integral, I have to remember my plus c. I'll drop this occasionally. Anytime I'm doing an indefinite integral, there should be a plus c here. You need to be careful on your quizzes and exams. You are being graded on those, so if you forget the plus c, I'm sure that's a point off. Okay. So I'm going to stop the video here. I forgot to start a timer, so I'm not sure how long I've been going, but this seems like a good stopping point so we can talk about the net change theorem. So let's go ahead and stop now.